Our first method is going to be Euler's method, so pronounced like the hockey team, Euler's method. The algorithm for it is nice and straightforward. It's very graphical in its idea. Here it is sketched out. We are given, we said we knew where we started, so we are going to be at the point t0, y0. This is t, that's y. We also said we have a formula for slopes at that point. So if I'm at that point, I can take this location, stick it into my function. Let's do it that way. Do it in green here. I can get that into my function, and I can get a slope. Because that's what my function gives me. I tell it t and y, it tells me the slope. All right. Then we take that slope, and we draw it. Here's my slope. Now we're going to do something with that slope that we have not done before. We are going to take that slope, and we are going to follow the straight line that's implied by that for exactly one step. So I'm going to draw the line here. There we go. One step of some very small time step, delta t. And as soon as we do that, we have turned all of our meta differential equation second-year math into, I've got a straight line with a slope. Yay, I'm back in high school. It's grade 9 math again. I've got a straight line, I've got a little step, and I want to figure out how far I went down when I followed that step. That'll be a delta y. And basically we're going to say, hey, there's going to be two updates I need to do. My time value that I started at, I'm going to add delta t. And so I'm going to get a new time value, which is my old time value plus delta t. My y value is going to be where I was before. So this coordinate here would be t1, y1. My new y value, so the next y value in this little underscore terminology here is my old y plus the slope times delta t. My new y is my old y plus the slope times delta t, but that actually comes pretty easily from, just erase this line for a second. What is slope? Slope is rise over run. Slope is delta y over delta t. I can rearrange that and find what delta y is, so I just bring the delta t up. So the slope times delta t is how much did my y change by. That's all it is. So my new y is my old y plus the change in y. And we just do that over and over again, because once I'm at my new location, I know things are a bit different here, but I can go to my slope formula, plug that value in, get a new slope, which might be slightly different, follow that for a time interval. Same, we're going to keep even time steps here, just to keep it easy for us. But we can imagine doing this calculation over and over again and generating a rough approximation of what would be a curve, but we're going to generate it by connecting little straight line segments together. And it all relies on having a formula for slopes, because a differential equation is just a formula for slopes, and a starting point where we can begin this journey of small straight line segments being stitched together. The MATLAB is going to look like this, because remember MATLAB arrays, hey, y sub 1, we can represent that. And remember what we're generating. We're generating a vector of t's, so this will be t0, t1, t2, these things here. Or in MATLAB speak, it'll be a little awkward, actually. We're going to start probably at t1 to make life easy, and then t of 2, t of 3, and so on. And this would be y of 1, because MATLAB arrays start at 1. But that would be the idea. I'm going to build these values, fill in my array as I go, and we're going to be able to generate those numbers that I need in the array using these formulas. So W91 is not an exciting file. I will grant you that. It is mostly setup stuff. So temperature external is whatever it is, K, dy, dt, that's fine. Initial temperatures. So this is all the stuff that we said we needed to get the simulation or the solving started. We're going to simulate for 100, whatever, I think the units are minutes here. And we're going to need to specify the number of intervals. I didn't really talk about that, so let's make a brief mention. What we're going to need here is, if we're going from t0 to t end, and we're going to divide it into n intervals, then delta t is going to be how long is this whole span all over the number of intervals, like so. And what we're going to do is do syntax very similar to ODE 45. So last week, we used something called ODE 45. I'm going to call it ODE Euler, just to make it look kind of the same. But notice the order. We have our differential equation, our formula for slopes as a function. Notice up there is defined as the and sign, ampersand, at sign, ampersand, ty. Then we're going to have our time span as a vector, our y naught, which is our starting value. And the one new thing here is, well, how many intervals do we want to use to divide this time span up into? And then we're going to plot when we're done. So we're going to build a t and y vector in our function. So we're going to look at ODE Euler, which is a scaffold here for us. And we're just going to try to build that up. Build empty t, y vectors. So one of the places to start is just to say, all right, I know what my final answer is going to be. It's a column vector full of t's. And I know that if I've got n intervals up here, how many values will define that number of intervals? N or n plus 1? Exactly. If you look at the notation, we said t0 to tn. That's because there's one more than number of intervals. So t is going to be a zeros vector. So n plus 1 rows, 1 column. Y is going to be a zeros vector, n plus 1 rows, 1 column. All right, fill in the starting values. What we know is that we're starting our t's at, and here we have to be a bit careful, t interval is actually 2 numbers. So how do I get the starting time value out of t interval? Let me just go back 1 sec. Actually, oh yeah, that's what we can do. We can comment that out. There we go. And then we can run it. So right now, t interval is this vector 0 to t end. How would I get the starting time out of that little vector?
It's t underscore interval at 1.
At 1. Exactly. It's t interval underscore interval at 1. T interval is a vector. And the first thing in it is the starting time. While we're on that same vein, let's figure out what delta t is. Well, it's the end time minus the start time divided by the number of intervals. How do I get the end time? In exactly the same vein.
Put end in there.
Ah, OK, end. Interesting. So let's try that. You're absolutely right. That would work. I think it's a little less obvious than the other options, though. Interval bracket end. That's the second. That's the end value. And then we can do minus the start value, which is 1. Oops. But let me ask for reference. How many elements are in this thing? Oh, yeah, thanks. This is t interval down here. How many elements has it got altogether? 2, right. So this is the important thing. Distinguishing the values from the number of values. No, this is important because especially for phase 2, you're going to get even more bookkeeping for almost all the project options. So there's only 2 elements in this. One of them, there's 101 things I'm going to build, but we're not there yet. This 0 and 100 is the array that has t interval. It's just 0 and 100. So I can grab the 0 by looking at the first element, and I can grab the 100 by grabbing the end element, yes, but I think it's more clear that we're talking about a really, really short thing here if we make that a 2. We will have a thing that's 101 long, but we don't have it yet. It's coming, but it's not there yet. So that's what I want to bring to bear right now. N plus 1 is our t vector, our y vector, absolutely. But t interval is just 2 little things. Start, end, done. So we need that, and we also need to take all that and divide it by n. OK. So just looking back to the math that we wanted to build up. So we've got a delta t, check. We're going to need this other stuff to happen here as well, so that'll be our next step. So, we also need y1. That was actually given to us in the top row. So let me just scroll up here. Someone told us that y0 was our first y value. And because the way MATLAB indexes things, it reads a little strangely, but my first y value will be y0. We've got dt. Everything else is pretty good to go. Then let's build the master loop. Because if we look at this process, it's a loop, right? I know where I am. I'm finding where I am next. I know where I am now. I find where I am next. And we know exactly how many steps there are going to be, because we said there are going to be n intervals. So we can predict, it's not a while loop, it's a for loop. I can say exactly how many steps I want to take. So let's just go for it. Do the simulation. Solving. So for I equals 1 to n, that's a good starting place. Now we just put in our concrete formulas. So literally, that second line up there, ti plus 1 is ti plus delta t. That's what we're going to do. T, I plus 1, the next t value. So we're starting at value 1. That's already defined. And we're constructing value 2, which is I plus 1. And then we add delta t. And yi plus 1 is y, the old y, plus the slope. And here it gets a little fancier. We'll do that in a second, times dt. So that, I'm just going to go back to the math for 1 second. That's this line here. My new y is my old y plus f of ti yi delta t. Notice it's the last time and the last y value, but we have formulas for that. That's just ti and yi. The translation, again, cannot get much more direct than this. That's it. That's Euler's method. Because once we've completed this loop, we will have filled in all the t values. We've had the starting one. We'll have filled in the next n. We'll have started at the y, a known y value. We'll have filled in all the ones after that. And we'll be ready to go. So we're going to try this just to see if it makes any sense at all. It's hard to test on its own. We need it in a context. So that's what our script W91 here gives us. It says, oh, solve the differential equation for heating and cooling. And before we run it, it behooves us to understand or take a guess at what's going to happen with this. Our external temperature is like today. It's -5. So let's say we took something out of this building at about our current temperature, y0 is 20. What's going to happen to it? It's going to cool down. And what kind of curve do we expect to see roughly shaped? Exactly, some kind of exponential decay type thing. I'm just going to go to the home here. Yes, so we're going to put a close all at the top here, as usual, so that the graph window pops up front. Doof. Hey, look at that. 20 degrees at the top, fantastic. -5 is the temperature of the environment, so things are cooling down, cooling down, cooling down, and we're getting something pretty reasonable out of this. So even though it's made up of straight lines, notice all these things are actual dots connected by straight lines, when you put them together in a gestalt, then it looks like a nice exponential decay curve. So that is our first non-black box solver. We gave it a rule for slopes. We were able to take steps, and on each step, using the slope, we could say where we would end up in the vertical direction, and we just repeated that until we got a certain length of time simulated.